I'm going to talk about the compact integrated Raman spectrometer. Thank you. And basically, this is a picture we all know about the Europa lander and the configuration that we were given. So we're going to be taking a sample cup that we are going to be handed, taking it into a sample chamber here, where we will analyze this in its original state. We may actually have this sitting outside in the cold, so we get as low as temperature as possible. But we like to look at the structure of the ice in its native form, and we like to melt that sample and do chemometrics to look at quantitatively what the salts and things that are in the sample. And finally, we want to desiccate the sample so that we dry down all the solid material to the bottom of this clear bottom sample holder so that we can look at it with our Raman spectrograph. Over here's a picture of our spectrograph, and I'll talk a little bit more about this. This is really based upon a design we already have that I'll show you later. And basically, it's the same size optics in this incarnation, but this all fits in box B, but we're likely to make this a little smaller as we mature the architecture over the next 2 years. So anyway, as I said, the idea is to bring things in its native form, look things in its solid state. This allows us to look at things like inclusions in the ice. When ice crystallizes, oftentimes things that are not ice are excluded and put in little grains that you can look at and identify, so you get a benefit of some concentration by doing that. We're interested in getting some quantitative idea of what's going on, so by liquefying the sample, we're able to do that. And finally, by desiccating the sample, by essentially letting all the water boil off, essentially, at the bottom, we'll collect all the sample and hopefully get some concentration in that mechanism as well. We have a 2D scanner in this architecture, which will allow us to scan and target any of the points throughout that volume. So this is the specs on the instrument. It's a 532 green Raman instrument that's been under development for, I think, 25 years. And we're using a single frequency laser that has a really good spatial mode. Focal spot is 20 microns or smaller, actually, and we can vary the power from 3 to 50 milliwatts to avoid burning the sample, so we can start low and move high and do that adaptively with the laser that we have. We use a high F-number laser, and I'll talk a little bit about the fact that this allows us to do a pencil beam, and we use F2 collection optics, which is, I think, one of the lowest F numbers of any Raman instrument out there to give us the optimal sensitivity. Working distance currently is 25 millimeters. We're going to try to scale that down as we, since the sample is being handed to us, as opposed to having the instrument on the end of a rover arm like it was originally designed. Since we have a cup, we don't have to have an inch of working distance, and this will allow us to scale the architecture proportionately. We can cover from 150 to 4,000 wave numbers, so this allows us to cover really low vibrational modes, cover the entire mineral fingerprint region, as well as the OH and CH stretches that occur beyond 3,000 wave numbers. Spectral resolution is just 6 wave numbers, and we have a signal-noise ratio of 5 or greater when we're 1 centimeter away from best focus. So one of the other features of the architecture is that it doesn't require you to autofocus in any way. And as I said, we're looking in 1 centimeter. We're going to have a spatial resolution, with native spatial resolution, with our context imager of 1504 by 2000. So one of the reasons to use green light is if you look at the absorption of ice and water, 532 is at the very minimum, and other wavelengths that you might choose are something like 7 to 10 times worse. Actually more than that. So green is an excellent wavelength to use. It is given you, a lot of people use 785. If you looked at the number of Raman spectrometers sold, 785 is the wavelength that people use, but rocks don't have very good Raman cross-section. So sort of the runner-up in terms of the pie chart of Raman instruments sold is green, and those allow you to interrogate things like minerals with good response. So because silicon detectors cut off at 1100 nanometers, by using 532, we're able to catch that higher beyond 3000 wave number region. It's very important for astrobiology applications. Let's see. We also avoid photo and thermal degradation by avoiding UV light, by keeping the power low, as low as possible to actually acquire signal. And we do have this issue. I'm sure everybody knows that there's concern over intrinsic fluorescence, laser-induced fluorescence with green light. So we're going to talk about a new technique that we have called serially shifted excitation to deal with that problem. So anyhow, this is a graph of the integration time as a function of focal distance, and you can imagine this going into your sample cup, which is about a centimeter deep. And what we know is that with dark pyroxene, we're able to maintain a signal-noise ratio of 5, and that's one of the weaker Raman scatterers that are around, so we use that as a benchmark. The pencil beam we have going into the sample has F15, which allows us essentially to be out of focus, yet still be on a small area, a relatively small spot, somewhere between 15 and 30 microns, all the way through the sample. But we use F2 to collect, even though we're out of focus, when we're not at best focus, over a centimeter, we're still able to see dark pyroxene. So this is an older incarnation of the instrument called MMRS. MMRS uses this kind of spectrometer based upon a holographic grating and a fiber input, and this is the probe head, which uses a laser that is contact bonded and actually doesn't work real well. It doesn't have any temperature control, so as it got colder in the atacamera, things didn't work out so well. As the temperature changed, you turn a laser on, it gets hot. The response changes, so we wanted to change the laser and work on this. This was a Category 1 instrument for MSL, but fibers caused a lot of concern, so that is, I think, fundamentally why this instrument was not selected for MSL, even though it was looked at in the early stages of the proposal development. So this is the current picture of the instrument. So I got rid of 2 fibers and then about 1,000 wires. No, only about 100. So these are the wires between a controller, which is a COTS-based instrument, and this is the Raman head. Here's the architecture. We start with a laser going through, light coming back that is longer than 532 is dispersed through the spectrometer and focuses on the back through a CCD. Light is shorter, it's illuminated by 467 nanometer LEDs. We also have UV LEDs, but primarily these are the ones that are used. This gives us a context imager. We implement light field imaging like Chris does, similar to what Chris does, so that we don't need to implement an autofocus either for the context imager. So here's a picture of some radiation testing we did with our JDSU laser, and so we ran it at 2 different currents. That's kind of hard to see, but we're seeing hardly any change. There's like a black shadow around this versus the blue for the 600 for red, and then for and so essentially you can see very little change, and you see the step-like behavior that occurs as you switch across modes of this laser. So it maintains single mode behavior over a wide distance, and it consists of a pump laser, a KTP doubling crystal, and a host crystal, the vanadate laser that lasers between these 2 places. So anyhow, this is the architecture of that laser. Because we have a birefringent crystal that's doing doubling, it also causes implementation of something called a LEO filter, which basically will vary its phase as you change the temperature. As you change the temperature of the laser slightly, what will happen is this will start allowing this mode or this mode or this mode or this mode to laze, and that's what's giving you the behavior here that we're seeing. So what we do is we use this because we know the Raman spectrum will shift with wavelength shifts, but the fluorescence, things fluoresce at the lowest excited state, and this allows to separate these two things. So we observe the raw spectra set for, let's say, 10 different samples. We look at that, and we mathematically solve for the fluorescence component separately from the Raman component. And we can show, here's some examples here of enstatite, and here we have Deinococcus radiodurans, which happens to have a carotenoid in it that is made without the use of light, by the way. And so this is a reasonable biomarker. And we can, because green is a longer wavelength than UV, you see longer molecules like carotenoids, and you can get resonant enhancement down to high femtomolar, low picomolar type concentrations. So we're also using light field imaging, and I'll try to skim past this, but since Chris talked about this, but we're able to essentially we can look at various planes all in one shot and do this without any moving parts. Just wanted to show an example of sort of what happens in terms of raw images. As you put the images together, you essentially can tell by looking at you cross-correlate these little subregions, and this allows you to get range information and allow you to ultimately stitch the image back together. And finally, this is our cameras. So we have two different cameras. Now we have to mitigate issues of radiation. So we're replacing what we're currently using, the 47-20 chip, with a much hard 347-20 chip. Same pinout, same electronics, lower voltages, bias voltages to make it operate. And so this has been developed by E2V, and so we're currently just essentially taking that chip and implementing electronics for it. It's very similar to what we already have. We can't use the KI-2020, which is in Mali, but it's just not going to work with radiation. We're replacing that with a CMOS CIS-115, which is used in Juno. And as I said, we love this architecture, but we're going to have to shift to special optics to make sure that they don't turn dark with radiation either. Here's two examples of the lasers. I talked about this one. This little tiny one we're also looking at that we just exposed to 10 times the radiation dose that's on Europa, and it's working great. So I think that's it. This is a summary that I'll let you guys read, but if I can answer any questions, that would be great. Thanks.
Any questions? Good.
Yeah. I particularly like the use of the shifted laser wavelength to address the fluorescence background. And amusingly, in another life, I spent about 30 or 40 years doing Raman spectroscopy. And way back about 1992, Andy Shreve was working on looking at photosynthetic reaction center resonance Raman, where the fluorescence is a real killer. Oh, and yeah. We invented a technique which we called shifted excitation Raman difference spectroscopy. CIRS. The acronym CIRS never really caught on because it's kind of ugly. But if you don't know about the reference, I'll give it to you.
Oh, I certainly know about CIRS.
Okay, yeah, okay.
So thank you very much. So that's sort of what started the whole thing going, is CIRS.
Oh, I'm glad to hear that.
You bet. Oh, by the way, I want to also just offer up that we are looking for MPP postdoc applications, which are coming due. So if any of your students or any students in this room would be interested in proposing, please call me. Okay. Thank you.
Excellent.